So, good afternoon, everyone. I'm just waiting for 5 minutes for people to join because I guess you are having the exam very soon. And if nobody will join in 5 minutes, then I'll start by myself so that you can see the recording afterwards. So, I'm just waiting till 3:05, you can say. Okay, so in the meantime, others will join. I am thinking of showing what is the major concern of today's class. Basically, just a minute. So, basically, in the last classes, Sir has talked about the third generation of solar cells, where he has talked about the organic solar cells. And in organic solar cells, if I give the recap, uh, then here he has talked about CDTE and all this stuff, and then the third generation, and then what are the organic solar cells and all this stuff, and how this conductivity of metal and semiconductors and others are different, and how this overlap is responsible for the conductivity. Okay, and in the last class he talked about the most important thing, except the organic solar cells, was the perovskite solar cells. So in perovskite solar cells he talked how it is formed, why is it important, and why it is more sold nowadays in the market. I mean, sold in the cells more of research purpose in the market. So all these 4 5 classes sir has already taught to you. I hope you have gone through it. So today I'll be showing you certain videos of how to fabricate a dye sensitized solar cell and how to fabricate a perovskite solar cell in the lab experimentally. And after that we will be practicing some questions on the basis of last week classes, because we are having the exam very soon. We are waiting 2 more minutes and then we can start. So in the meantime I can show you this. We'll start at 3:05.
Okay, sir.
So I guess this is the last class of ours. So I hope you have learned something from this course.
Sir, in your first class, I think you are in the same room.
Yeah, actually in the first class I was in the same room. This is
Yes,
this
yes,
is the glow box behind me.
yes, sir. Yes, sir.
So are you guys ready for the exam? Okay, so we can start now. So as you know, this is the assignment number 8 on the basis of week 8 classes, and I'll be discussing certain questions. And before going to the questions and discussion of the assignment, I would like to show you certain videos. The first video is regarding how to fabricate a dye sensitized solar cell in the lab. and the second video is regarding how to fabricate a perovskite solar cell in the lab, so that you guys get a feeling, because it is the last class, so I just wanted to show it to you. So I just made a YouTube recording of some different parts.
Titanium dioxide.
Is it audible, Mele?
Yes, sir. Yes.
Okay,
Suspension.
have a look.
Step 1. Start with 6 grams of titanium dioxide powder in a mortar and pestle. Under a ventilated fume hood, slowly add vinegar in 1 milliliter increments to the solution, grinding well each time. The process should take around 30 minutes and will result in a very white, milky, paint-like solution. Step 2. Add a drop of clear dishwashing liquid to the solution, but do not grind, otherwise it will get foamy and bubbly. The dishwashing liquid will act as a surfactant, which reduces the surface tension of the solution and thus of the solution and thus helps it coat the glass plates more evenly. Step 3. Use a funnel to pour the solution into the small dropper bottle. Leave the solution alone to equilibrate for at least 15 minutes. Part 2. Coating slides with the titanium dioxide suspension. Step 1. Clean 2 conductive glass slides by rinsing them with a wash bottle filled with ethanol. Gently dry them with a soft tissue. Step 2. Use a multimeter set to resistance, ohms, to check which side of the glass slide is conductive. The slide should conduct between 10 and 30 ohms on the conductive side and nothing on the non-conductive side. There should be a slight visible difference between the conductive and non-conductive side.
Yeah, so first what we do, we make sure that which the FTO or the ITO, whatever we are using, which is the conductive side and which is the non-conductive side, and we generally use the FTO for that. Okay,
Slides as well. The conductive side will appear bluish and cloudy, while the non-conductive side will appear clear and yellowish. Step 3. Use a transparent tape to tape 1 glass slide down on the table on all 4 edges.
it is not visible. Nothing is visible. Oh, just a minute. I'm so sorry. I guess I've not presented. Why you guys were not showing anything? Just a minute. Okay. Now is it visible? Just a minute. Now is it visible? Hello?
Yes, sir.
Okay. I'm so sorry. I'm starting it again. Just a minute. Now you can see.
Titanium dioxide suspension. Step 1. Start with 6 grams of titanium dioxide powder in a mortar and pestle. Under a ventilated fume hood, slowly add vinegar in 1 milliliter increments to the solution, grinding well each time. The process should take around 30 minutes and will result in a very white, milky, paint-like solution. Step 2. Add a drop of clear dishwashing liquid to the solution, but do not grind, otherwise it will get foamy and bubbly. The dishwashing liquid will act as a surfactant, which reduces the surface tension of the solution and thus helps it coat the glass plates more evenly. Step 3. Use a funnel to pour the solution into the small dropper bottle. Leave the solution alone to equilibrate for at least 15 minutes. Part 2. Coating slides with the titanium dioxide suspension. Step 1. Clean 2 conductive glass slides by rinsing them with a wash bottle filled with ethanol. Gently dry them with a soft tissue. Step 2. Use a multimeter set to resistance, ohms, to check which side of the glass slide is conductive. The slide should conduct between 10 and 30 ohms on the conductive side and nothing on the non-conductive side. There should be a slight visible difference between the conductive and non-conductive slides as well. The conductive side will appear bluish and cloudy, while the non-conductive side will appear clear and yellowish. Step 3. Use a transparent tape to tape 1 glass slide down on the table on all 4 edges. The tape should cover roughly 1 millimeter of the slide on 3 of the edges and about 4 millimeters of the slide on the remaining edge. This tape has a controlled thickness and will form a 40 to 50 micron deep channel into which the titanium dioxide suspension can flow. Step 4. Use ethanol on a tissue to wipe off any fingerprints or oils on the slide. Step 5. Put a drop or 2 of the titanium dioxide solution on the slide and quickly spread the solution as evenly as possible over the slide using a clean glass stirring rod. Step 6. Wait for the slide to dry for a few minutes before carefully removing the tape. Part 3. Annealing the coated slides. Step 1. Anneal the titanium dioxide film on the glass slide in a fume hood or well-ventilated area. Use one of the following methods. 1. Make a simple tube furnace from a hot air gun. Start by removing the outer plastic casing at the base of the nozzle to prevent it from melting, then wrap aluminum foil around the nozzle to form an enclosed oven. The slides will lie flat inside this oven for the annealing process. Be sure to leave a small opening in the foil so that you can watch the slides for color change as they anneal. Turn the hot air gun on high or to 450 degrees Celsius. Let heat for 30 minutes. 2. Place a ring stand over an alcohol burner. Anneal the slides one by one by resting them on the ring stand at the tip of the flame for 10 minutes. Step 2. Watch the slides as they anneal. The titanium dioxide coated section should turn purplish brown, then back to white, as the heat burns off the surfactant. Step 3. Store the slides for later use. Part 4. Staining the titanium dioxide with anthocyanin dye. Step 1. Use a clean mortar and pestle to crush 3 to 4 berries. Transfer the crushed berries to a petri dish. Step 2. Add about a tablespoon of distilled water to the crushed berries and stir with a clean glass rod. Step 3. Place the slide face down into the berry mixture so that the titanium dioxide coated section is submerged in berry juice. Step 4. Let the slide soak in the juice for 10 minutes. The film should be stained bright purple. If you can see any white titanium dioxide remaining on either side of the glass after 10 minutes, put the slide back into the dye for another 5 minutes. Now is a good time to start on Part 4, carbon coating the counter electrode. Step 5. Lift the slide out of the juice using a pair of plastic tweezers. Rinse the slide first in distilled water to remove any fibrous debris from the berries, and then in ethanol to remove excess water from the porous titanium dioxide coated section. Blot the slide dry with a tissue. Step 6. You have now made a titanium dioxide dye-sensitized electrode. If the slide is not going to be used right away, store it submerged in distilled white vinegar in a closed, dark-colored bottle. Part 5. Carbon coating the counter electrode. Step 1. While the titanium dioxide electrode is being stained in the berry juice, make the counter electrode from another piece of conductive glass. Step 2. Light a tea candle with a match. Step 3. Determine which side of the clean glass plate is conductive with a multimeter set to resistance, ohms. Hold the slide by one edge with the metal tongs. Pass the conductive side through the middle of the flame until the entire side is coated evenly with soot, except for where the metal tongs were. Step 4. Place the carbon-coated slide face up on the counter. Be careful, the slide will be hot. Allow it to cool. Then, use a tissue and cotton swab to clean any residual soot off the edge of the slide covered by the metal tongs to clear the carbon off a 4mm strip. This edge will be where the alligator clip attaches. Step 5. You have now made a carbon-coated counter electrode. The carbon coating on the slide is very fragile and is easily rubbed off. Be careful not to touch it. Part 6. Assembling the solar cell device. Step 1. If the stained titanium dioxide glass slide has been stored in vinegar, carefully remove it. Rinse the slide with water and then with ethanol. Then, gently blot it with a tissue. Step 2. These two slides, the titanium dioxide coated slide and the carbon coated slide, will be sandwiched together to make a solar cell. Both slides have a 4mm strip on one edge that is clear of any coating. The slides must be assembled so that the coated areas of the slides are touching each other completely. This means the slides will be offset and the 4mm empty strips will be exposed on each side. These two exposed edges will serve as the contact points for the negative and positive electrodes. Step 3. Place the dry titanium dioxide coated slide on a flat surface so that the titanium dioxide coated section is face up. Place the carbon-coated slide face down on top of the titanium dioxide slide so that the coating completely covers the titanium dioxide coating, leaving a 4 mm strip exposed on each slide. Step 4. Pick up the two slides in this orientation, being careful not to let them move. Clip the edges, the ones that do not have the 4 mm strip exposed, together on both sides with two binder clips. Step 5. Place 1 or 2 drops of the iodide electrolyte solution at one of the edges of the slides. Step 6. Alternately open and close each side of the solar cell by releasing and returning the binder clips. The liquid is drawn into the space between the electrodes by capillary action. This wets the stained titanium dioxide film. Make sure that all of the stained area is contacted by the electrolyte. Step 7. Wipe off the excess electrolyte solution from the exposed areas of the glass using cotton swabs and tissues dampened with ethanol. The cell will not work well if there is any electrolyte solution left on the exposed areas where the alligator clips attach. Step 8. Fasten alligator clips to the two exposed sides or poles of the solar cell to make electrical contact to the finished device. Part 7. Measuring the electrical output. Step 1. The completed solar cell can be taken outside and measured under sunlight. The cell will last longer if it is protected from the elements by a polycarbonate plastic cover like a plastic petri dish. Sun and air will dry out the iodine electrolyte solution inside the cell, which will speed up the deterioration of the dye molecules in the berry juice. Step 2. For instructions on how to measure the voltage and amperage of the cell, see Experiment 1, Measuring Voltage and Current.
So did you guys see this was the fabrication process for the dye sensitized solar cells basically, and how do we measure the current in presence of sunlight? And I have recorded another video which shows the fabrication of perovskite solar cells, and then I have few questions, 8 to 9 questions for the assignment 8 that we will be discussing. So as it is our last class, I would like you people to see this video also, that is regarding the fabrication of perovskite solar cell. That will really give you a lot of interest. So pardon me if there is something wrong. And is it visible? Malay, the screen is visible?
Also some mixing scheme is visible.
Just a minute.
Yes,
The
now
device
okay.
that converts sunlight into
okay.
electricity.
Okay.
Yes.
The cost
This
of
is
fabricating
perovskite solar
one cell
cells.
is
Have a
less than
watch.
50 cents. It only takes a few hours, and we use standard laboratory equipment. This experiment is highly appropriate for general chemistry students to learn about this state-of-the-art renewable energy technology. The perovskite layer absorbs light and creates electrons in the conduction band and holes in the valence band. On one side, titania selectively transfers electrons from perovskite to the FTO anode. On the other side, copper thiocyanate selectively transfers holes through the carbon particles to the FTO cathode. Once we have electrons on the anode and holes on the cathode, we can hook it up to power an external device like an LED. First, we are going to use a model to demonstrate the fabrication of the solar cell. We start by placing an FTO glass with the conductive side facing up. Next, we deposit a layer of titania covering 3/4 of the surface. Then we coat the surface with perovskite light absorbing material, followed by a layer of copper thiocyanate. To complete the device, we sprinkle carbon particles on layer and close it with another piece of FTO glass with conductive side facing down. We use binder clips to hold the device together.
To make a perovskite solar cell, we need 2 pieces of FTO glass, titanium, perovskite, copper thiocyanate solutions, and carbon powder. To prepare the titanium solution, we use 5 ml of ethanol, 0.3 milliliter of titanium isopropoxide, and 0.1 milliliter of hydrochloric acid. After adding the three together, we let the solution stir at room temperature for about 10 minutes. The second solution we have to prepare is the light-absorbing material perovskite. To make a 0.5 molar perovskite solution, we will need to mix 140 mg of lead chloride and 240 mg of methyl ammonium iodide in 1 ml of dimethylformamide solvent. The resulting reaction needs to be stirred at 80 Celsius until a homogeneous yellow and transparent solution is formed. Lastly, we will make 0.05 molar copper thiocyanate solution by stirring 6 mg of copper thiocyanate powder in 1 milliliter of dipropyl sulfide solvent at room temperature overnight. The final solution should look colorless and transparent.
In the first step, we will determine the conductive side of FTO glass. To determine the conductive side, we set the multimeter to resistance mode, plug the two leads into the multimeter, and measure the sheet resistance on each side using the probes. The uncoated side will not give any value. To deposit the titania layer, place the FTO glass on the benchtop with the conductive side facing up. We deposit 1 drop of titania solution onto the glass and spread it across the surface with a glass pipette. Then we remove the tape entirely and place the glass piece on a hot plate facing up. We heat it at 450 degrees Celsius for about 20 minutes and let it cool down for about 10 minutes. We put 1 drop of perovskite solution and spread it across the surface with a pipette. We roll the pipette over the glass several times to create a uniform, smooth film. We keep the uncoated surface covered and remove the excess tape. We place the glass piece on a hot plate preheated to about 110 degrees Celsius. We wait until the film turns completely black and let it sit there for another 10 minutes. We deposit 1 drop of copper thiocyanate solution and quickly spread it across the surface with a glass pipette. Now place the glass piece on the benchtop, scoop a small amount of carbon particles with a spatula and sprinkle them onto the glass piece. Finally, we close the device with another piece of FTO glass with the conductive side facing down, and we hold the device together using binder clips.
We measure voltage by turning the multimeter knob to the 2 volt mark. We measure current by turning the knob to 1 milliampere mark.
So yes, that's all. So I guess you people will be a little interested after seeing it, that how do we fabricate the perovskite and the dye sensitized solar cell in the lab. So the procedure is more or less same, but yeah, one thing that we take care of is nowadays what we do the reaction inside the globe box in the inert environment, so that no other environmental factor should play a major role and we get more and more efficiency. So nowadays we are mostly working on fabricating the 3rd generation solar cells, and soon you will see the cells that will be in the market are will be the multi-junction, that is the junction of perovskite or the quantum dots, or the junction of perovskite and the dye sensitized solar cells. The advantage with the perovskite solar cells are that you can tune their band gap according to your, like, you can tune their properties, but they are not very stable, but they can give you good efficiency. So in order to make them stabilize, people are trying to make their heterojunction with other reported form of solar cells in the 3rd generation. So this was regarding giving you a little bit interest because it is our last class. Now let's move to the assignment today. So The assignment is today is like this. I will be having this around 8 questions based on 8 week 8 classes, and you can tell me the answer. If not, then I'll show you the solution, and I'll be sharing the solution anyways on the screen anyways. So yeah, just a minute. So the first question is, the photoelectrode used in the dye sensitized solar cells is or are. It could be a one answer, it could be a two answer. Options are nano SNO2, platinum, nano ZNO, or nano TiO2, or NiO. Tell me the answer if you know it.
Sir, C and D.
Who is it?
C and D.
Okay. Who is it? Just a minute. Some people are writing in the chat box also, so I have to see it. Okay. So Vaishnavi is saying C and D, and it was you, Melee, right? Okay, Melee, Vaishnavi, Gaurav, Ajay are there. So yeah, C and D. You are saying C and D as nano ZNO and nano TiO2. Yeah, we know that what do we need as a photoelectrode. It's a very straightforward question. So yes, the options are C and D. It is right. Okay, let's move to the second question. I'll share the PDF anyways. Will be you. The primary light absorbing material used in the perovskite solar cells are BATiO3, MAPBI3, MAPBF3, CATiO3, or SRTiO3. What could be the right answer?
I think option B.
Option B. Who is it?
I think, I don't know, I'm not sure, sir. I think option B.
Okay, Gaurav. Do you know Gaurav, Ajay, Vaishnavi? Anybody? Okay, just to tell you, I think somebody is trying to join. Okay, Vaishnavi and Ajay are saying C. Okay, you guys are saying C. So why not it could be B. Vaishnavi and Ajay, why it cannot be B? Like, okay, let me tell you. First of all, one thing is quite clear to you guys, which is that we generally use the perovskite halides. Sir has already told you about the structure of a perovskite. Like, it is generally AbO3 or AbX3. What is A side, what is B side? So okay, let me tell you, there are two more important factors just for your knowledge. It is not to be deal with your exam. There are two factors. One factor is called as Goldschmidt tolerance factor, and the second factor is called as octahedral factor. So in order to lie in the domains of perovskite, the Goldschmidt tolerance factor need to be in between 0.8 to 1. Okay, and the octahedral factor also has some definite value. Now first thing is sure, in perovskite solar cell we generally use perovskite halides. So basically two halides are there, MAPBI3 and MAPBF3. Now amongst them, which is the better light absorbing material? The one which will be having lesser band gap and more Goldschmidt tolerance factor. Let me show you what is Goldschmidt tolerance factor just for your knowledge, so that you may let me show you if it is available in Google. I have not made any slide for it anyways. Yeah, so basically this is the formula of Goldschmidt tolerance factor. If you consider AbX3, Ra plus Rx over root 2 of Rb plus Rx, and it should lie in between 0.8 to 1 for the cubic domains. Basically the tolerance factor 0.9 to 1 for the cubic domains to lie in terms of perovskites. So in terms of perovskite, if you see this fluorine atom is not having much good orbital overlap. So the iodine having a bigger size is after hybridization creates this orbital in such a form that it is a more better and stable light absorbing material. So the correct answer is V. Let me show you the answer so that you guys can understand. The correct answer is B. The correct answer is MAPBI3. Okay, the MAPBF3 is not a right answer. Go through these questions. It can come in the exam as it is. Okay, so yeah, it is MCQ as far as I know, and I can email you afterwards also. Did you not check it with Ajay, with Hari Shankar or these people? Hari Shankar actually stays with sir. As far as I am given information, it will be mostly MCQs. But still, if you want, you can email me. I'll let you know after asking sir if there are some changes. But it is MCQ and MSQ. It could be MSQ also, like this question was there, nano ZNO or nano TiO2, but the question will be mostly MCQs and MSQs. Okay, now let's move to the next question. Question number 3. Question number 3 is saying following properties of perovskite materials are beneficial for their use in solar cells. The options are stability under ambient conditions, and low defect density, high absorption coefficient, long charge carrier diffusion length, or short carrier diffusion length. What do you guys think? What could be the possible right answers?
Sir, C and D.
Okay. Could you explain why?
Right, band gap is more, sir. If we create the material, that's why absorption, high absorption coefficient. And sir, carrier lifetime is high, that's why long carrier diffusive length.
Okay. Fine. I mean, these are some learning terms. You have just learned it. But still, let me tell you. Absorption coefficient means what? See, there are many terms. I have shown you in my previous classes. I have told you a website, PB Education. There you can see there are many losses which takes place in solar cell, and they are generally like they could reflect the light, which is reflectance or transmittance. That means less and less light get absorbed. So the material which can reflect more light, that means which absorb less light, are not a good material even in the perovskite domain. Now if we talk about perovskite materials, they are beneficial to use in solar cells because they have very less reflectivity and they have high absorption coefficients. Because if you see, I think it is 5p and 4f orbitals of this lead and this bromine or the halogen atom, which intermix together in such a form that it lies in a region that provides the epsilon value very high, which means it gets the very high absorption coefficient. The perovskite generally have very high absorption coefficient, and because of having very high absorption coefficient, that means more and more formation of electrons and holes will be there. If more and more formation of electron and hole will be there, that means more and more I don't know who tried to join. Okay, more and more electron formation will be there, and if more and more electron and hole formation will be there, that means more and more charge carrier will be formed, and as more and more charge carrier will be formed, electron hole forms, electron hole forms, electron hole forms, electron hole forms. That means the charge carrier length will be bigger. So obviously the options which are right are C and D, the high absorption coefficient, the charge carrier lifetime. Okay, and just to give you a feeling of this, let me show you this website. Keep on following this website whenever you get time, because this is a really important website for you people. If you go here in solar cell operation, and see, the reflectivity thing that I was talking about comes in this optical losses, which I have already told you in the last class. The more and more surface reflection will be there, the lesser will be the contact, and this will get reflected more, and hence less light can be entered into this. and if hence less light will be there, that means trapping will be less. So this is how we form it actually. And if we talk about the recombination losses that take place, what happens generally is this. If you see here, yeah, okay, if you can see here, as the light falls, photon generates an electron and hole pair, and this electron and hole pair recombines at the top surface. Okay, now a photon generates an electron hole pair deeper, and this keeps on forming and forming. So higher the absorption coefficient, higher will be the like this photon will transmit it, and higher will be the carrier diffusion length. So it keeps on forming and forming and forming, and then at last it will come here, and then this will recombine. And if you provide a load here nearby connecting this all, then this will start illumination. This is how a minority and the majority carrier work. Okay, so then the electron recombines at the rear part. Let's move to the next question. The next question is saying the dopant added to polythiophene to make it conductive is FeCl3, NS4Cl, SN2CF3 minus, SO3CF3 minus, or ZnCl2.
Option D.
SO3CF3 minus. Why is that?
Yes, sir. Sir, that taught in class.
Okay, who got?
Dopant is used.
Yeah. So why SO3CF3 minus? Why not NH4Cl or FeCl2 or ZnCl2? Okay, just for your information, like the answer is right, but when we dope something, no, Malay or whoever it is,
Pi. Sir, moving the pi bond weaker,
okay,
we make that dopant in organic semiconductor like sulfur. Suppose in benzene ring sulfur dope to dissociate the pi electrons, pi, to weaken the pi bonds, so that carrier will go to one state to another state, so electron will get to the resin.
yeah, right, you're absolutely right. And secondly, one more information that I want to give you. What is the concept of doping basically? Yes, you said it right, very right. The answer is also right, I guess. But I want to tell you one thing. The one thing, that information that I wanted to give you is that when you dope something now, you dope something on the basis of the the alignment of the valence band and the conduction band. Okay, suppose you are doping something which is not lying along with the valence band and conduct. Okay, let me show you and talk you with the pictures, because all these questions are theoretical base. I didn't know, but what will be the explanation? So let's see the band structure of perovskite solar cell. Okay, so if you see this figure, if you are seeing this figure, you see this balance within conduction band is there. So this is PbI2, this is something, this is something, this is p-type material, this is n-type material. So if I am going to the images, let me show you. Yeah, you see this image. So this is perovskite, and this is CDS layer below this, and this is p dot PSS layer. Now in order to make the movement of electron and hole facile, we have to choose a electron transport layer and a hole transport layer in such a way that its valence band should lie near to this level, and its conduction band should lie to the conduction band of this level. Okay, now the same concept lie when you dope something. When you are doping something, no, you have to choose a material in such a way whose valence and conduction band lie near to the material conduction band, valence band, or the homo-lumo gap, so that the electron transfer and the hole transfer, the electron movement and the hole movement is facile. Okay, so like your answer is right for polythiophene, this is the right answer. But just to give you a taste of the answer is SO3CF3 minus. But just to give you a taste of how to approach a new material, these are the things which we have to keep in mind: the position of valence band and the conduction band, or the homo and lumo. Now how do we find the position of valence band and conduction band? In order to find the position of valence band and conduction band for semiconductors, generally we do UPS spectra. In UPS spectra, we get the position of the conduction and valence band in terms of these energies. Okay, and from here we find out the plots. And in case of organic compounds, we do the CB spectra. cyclic voltammetry. In CV spectra, we generally get the HOMO-LUMO gap, and accordingly we can choose a material. I'm telling you things which can go above your mind right now, but if you see from this HOMO-LUMO gap, we can find out the conduction band and the balance band or the HOMO-LUMO from the CV curves. So these are the things which we keep into mind while we are doping something. I mean, I don't know you're able to understand or not, but yeah, I just wanted to give you a taste or a flavor, or at least made you familiar with the terms like CV spectra or UPS spectra, and what is band gap and how do we choose a material to dope. In perovskite, this is how it works. So your answer was SO3 CF3 minus. Let's move to the next question. The next question is saying that the photosensitizer used in the dye sensitized solar cell should have high ionic conductivity, high electronic conductivity, high band gap, or low band gap. Tell me the answer. Anyone? Question number 5. The photosensitizer used in dye sensitized solar cells should have what?
Low band gap.
Okay. So, and why do you think so? Why do you think so? Okay, so first of all, do you know that what is the basic role of a photosensitizer is? So basically, you know what they do. The main role of a photosensitizer is that the absorption of the solar photons and the injection of the photoexcited electron into the conduction band of the n-type semiconductor. Okay, when you are making a NIP junction and you have to choose a photosensitizer in such a way that more and more absorption of the solar photons can be there, and then it can be injected in the photoexcited state into the conduction band of the n-type semiconductor, and more solar photons can be generated only when the band gap is lower. Okay, so yeah, the correct answer is right, lower band gap. I guess I have missed from the class. Just a minute. Okay, I guess I missed out somehow due to connectivity issue. So the correct answer was right. The correct answer was lower band gap, and I have told you why the correct answer is lower band gap, because just a minute, let me present my whole entire screen. Okay, the correct answer was lower band gap, and the correct answer was lower band gap because you know the role of photosensitizer is the absorption of solar photons and then induction of the photoexcited electrons into the conduction band. So basically the lesser will be the band gap, the more and more will be the absorption of the solar photons, and then more and more correct current could be generated. Okay, so now let's move to the next question. The next question is saying bulk heterojunction solar cells have superiority over bilayer organic solar cells due to, and the options are relatively thinner absorber layer, or better dissociations of excitons, or better interfacial contact between donor and acceptor phases, or lower optical absorption.
I think B and C.
Better dissociation of excitons and better interfacial contact between donor and acceptor
Donor
phases.
and acceptor, yes.
Okay, so first of all, why thinner absorber layer is not good?
Sir, because the wavelength of high band gap will not, the wavelength greater than Eg will not penetrate and not absorb. That's why.
Yeah, that is right. But okay. So basically, see, Malay, we are comparing here in heterojunction and bilayer. So in bilayer, what we do, we have a layer over layer. In heterojunction, what we do, we have two layers, and then we make a heterojunction in between them, so that in the grain boundaries they have two different phases. Like there are two different phases which are present all together, but the layer is same. Okay. So now what happens? They are superior because not because they are having relatively thinner absorber layer, but because of the heterojunction formation in between them, they have better dissociation of excitons, because both the properties, the property of one layer and property of the second layer which is forming a heterojunction, both are coming into picture, and due to this interfacial contact between this donor and acceptor phases which is forming heterojunction, it shows better efficiency and better fill factor. So yeah, the correct options are B and C, I guess. Let me give a check also. Yes, you're right. The correct options are better dissociation of excitons and better interfacial contact between donor and acceptor phases. For those who are missing it out, I will be sharing the assignment and also uploading the YouTube. Yeah.
Sir, the answer is not clear to me. Why relatively not thinner absorber?
See, yeah, definitely. Okay, I'm telling
actually,
you.
Sir, this bulk heterojunction is mixing is done by nanoscale. It's very nano. It is, I think, total material is very thin. Nanoscale means material is very thin.
Absolutely right. You're right. You're right. See, what happens when we are doing the spin coating of something? We generally nowadays what we do when we make a solar cell, we do the spin coating. Now, what heterojunction means? What are you able to understand? What is the meaning of heterojunction, Malay? Okay, just a minute. Let me show you something so that you can understand more. Heterojunction FT, so that you can understand better. Yeah, here it is. See, this is a heterojunction of BiVO4 and TiO2. So this is a junction there, and in this junction, suppose one is acceptor and one is donor. Now this junction is there, and because of this donor and acceptor layer, both the properties can be found here. Okay, so generally when we make a heterojunction, they are relatively thinner, but being thinner is not a reason of them to show good properties. Now if you coat this TiO2 over BiVO4, for example, if I show this bilayer solar cells, that means you are having a layer over layer. Okay, when you're having a layer over layer, that means you are making it more thicker, but this thinner and thicker, because they are in the nano design, are not making much difference. But in that case, the surface which is exposed more to the anode or the cathode side, or the surface which is more exposed to the sunlight, will show more property of it than the surface which is lesser. So both, I mean, you won't be able to show the properties of both of them together. How should I say you that you know the concept of hybrid means, suppose you have a lion and you have a tiger. Okay, now a lion give birth to a lion only and a tiger give birth to a tiger. But if you want to have a progeny which shows the properties of both, then you make a cross in between lion and a tigress, then you may get a liger or a tiger and a lioness. This is how it works. Okay, so in order to get the best property, you make a heterojunction. So when you make a heterojunction, that means you get better dissociation of excitons, because this absorption, that is donor and acceptor phases, this absorption and desorption both are happening in the same interfacial contact. Which is the interfacial contact? This is the interfacial contact which is present there, which is absent in this interfacial contact, which is absent in the bilayer solar cells. So this is the reason. Are you getting me?
Yes.
Okay. Now let's move to the next question. The next question is, satellite power requirement is provided through. The options are solar cells, dry cells, nickel cadmium cells, or lead acid based batteries.
Solar cell.
Yeah, it's a very quick and obvious question, and this is what is the most important form of energy which is available in the space. So yeah.
Sir, in satellite, gallium arsenide.
Yeah, gallium arsenide and all these.
Arsenide.
Yeah. But we are trying to figure out some more stable materials now. I mean, people are working hard, because now to space stations are also being made in the space. Now, I mean, you must be knowing Elon Musk. He is planning to open a space station and a space hotel in the space.
Right.
Yeah, so it will be a tourist spot for people who can visit there and stay in the space, and all this into all these things, the energy will be provided through this solar domain. I mean, solar energy is the best and a versatile form of energy. So yes, yeah, right. Okay, so let's move to the last question of today. The last question of today is saying that the efficiency of a solar cell is 20% and its surface area is 4 centimeters square. Find the electrical energy generated in 1 second by 3000 cells connected in a solar panel if 640 joule of solar energy is incident on 1 meter square area in 1 second. I am not giving you any option, you give a guess, then I will show you the answers. I am giving you 3 to 4 minutes for this. जहाँ के महल Okay, so as I'll show you the answer now.
So actually,
Hmm.
efficiency equals to V into I by power input. Okay, sir.
Hmm.
So V in power input is equals to 640 into 1 meter square into 4
Hmm.
centimeter square total area into 100. And efficiency is 24. By that I have to find the power. This is the formula, I think.
Yeah, if I am able to understand right, you are saying it right. Let me show you the solution, anyways.
Yes.
So the correct option is V. Oh, I have not given you any option, right? Okay, so yeah, the total surface area of the solar cell in which solar energy is falling is the area of the each cell into the number of cells. So we have been given that the number of cells 4 and the surface area is 3000 cells are there, and the surface area of each cell is 4 centimeters square. So if we multiply that, then we get 12,000 centimeters square, which is 1.2 meter square. Now the solar energy falling on 3000 cells will be the solar energy falling on this 1.2 meter square area, which is equals to 1.2 cross 640 joule. If it is an incident energy on 1 meter square area, then what will be the energy on 1.2 meter square? That means 640 into 1.2, which is 768 joule. Now the energy converted into electrical energy will be 10020 cross 768, which is 153.6 joule. Okay. No, I think this will be 12000. I have made some mistake here. This is 12,000 centimeters square into 768. That means 153.6 joule. Okay, so this is how it works. So anyways, I will be sharing all these answers just to remind you all. Every assignment I am sharing, this is a drive link for the backup within an assignment solution PDF. This is the YouTube channel link, and this is a website which is of best use. If you have any issue, then you can go to the drive, you can download the video, you can download the assignment PDF from this link, and this is a YouTube channel. If you want to see the video again, you can go to this website, and if you want to know in detail, you can go to this website which is having all the detail of the solar cells. So once more, let me copy this link to the people if anybody is not able to follow. This is a drive link. And this is a YouTube channel link. Today's video will also be uploaded there, and the rest of the previous videos of all the assignments are being uploaded there. And this is the website PB Education, which is having all the basic to the characterization to fabrication to the concept, everything in detail and in video format. If you want to learn something, or if you have any confusion, you can go through it. You will be able to clear your doubts very easily from this website. And you can find this assignment in this drive. If you will open this drive, then you will see that such a link will open, where all of us, Ravish, me and Harishankar, are constantly uploading our presentation and the backup video and the YouTube channel link week wise. You can see week 1, week 2, week 3, week 1, all three of us, Ravi, me and Harishankar, all of us are uploading constantly, and today's video will also be uploaded. Week 8 video have been already uploaded by Ravi. I will also be uploading now. So this is how it is going on. And if you have any further doubt, feel free to email me afterward. And if you want to know something out of this course related to the research in this field, you can contact me anytime. Okay, Mele, it was really nice to talk to you in the whole classes. You were very active. All the best for the exam, and if you have any confusion, email me. Okay.
Okay, sir. Thank you, sir.
Okay, then everyone, all the best for the exam. And if you have any email, kindly, if you have any doubt, kindly email me. Then see you, take care, and all the best. Do good learning. Yeah, thank you, Vaishnavi. And you, if you guys know my email, right? This is my email ID. Just for the sake, if you don't know, note it down. sd19ip011 @isercole.ac.in. Okay, thank you then.